Hello, everybody, and welcome to WOW 11. Today's webinar, Misalignment and Shaft Preload in Turbomachines, is brought to you as a part of Mobius Connect's week of webinar series. I'm Kim Fugger, the moderator of today's session, and I am excited you are here. Now, this webinar is going to be recorded, and you will be emailed a link with the access to the on-demand version of the webinar. Now, WOW, or Week of Webinars, is a free collection of one-hour educational presentations delivered by industry practitioners from all over the world, and it's all happening this week. We encourage you to attend as many presentations as you would like, get all of your questions answered live, and earn your education credits as well. And before we jump into today's presentation, I would like to review a few resources with you. The Mobius Connect community platform is all about you, providing you with the space and technology to connect with the right people and resources to help you solve problems, continue learning, and share your experiences as well. Once you've logged in or created your free profile, like other professional networking sites, you can start connecting with other industry professionals wherever you are in the world and in any language. Mobius Connect includes fun features like the industry's live feed, forum discussions, interactive connection finder map, direct messaging, and customized communication based on your areas of interest. We have global events, jobs, and news listings, and a mobile app, which is available in the Apple and Google Play stores. You can continue your educational journey throughout the year on CBM Connect and Reliability Connect. There are hundreds of quick videos, articles, webinars, and interviews. Now, for those of you just joining us, welcome to Misalignment and Shaft Preload of Turbomachines, presented by Salah Attia. Well, welcome, Salah. How are you?
Good, thanks. Thank you so much, Kim.
Yes. Now, if anyone does have any questions for Salah during the webinar today, type them in the question panel of your screen, and Salah will be more than happy to answer your questions live on the air. Your questions will be aired anonymously, so no need to feel like you're getting called out. And if we happen to not run or we do run out of time and we don't get to your question live, Salah will follow up with your question right after the webinar. All right, Salah, we're going to go ahead and pass the presentation over to you.
Excellent. Hello, everyone. Welcome to meet you. My name is Salah Attia. I'm a condition monitoring specialist and I'm a technical consultant. And I'm a VCAT4 vibration analyst from Mobius Institute. And I'm working in this field for almost like 15 years or 16 years now. And today I'm going to talk with you about the shaft preloads in Turbomachines. And I'm not sure, just 1 second. Yep. This part, which is the shaft preloads, is a part of the Advanced Turbomachinery Analysis Training course by MDI, or Machinery Diagnostics Institute. I started to write this course like 3 years ago. And in this course, we're talking about the machinery, the measurement sensors and its application, the sensor types, the accelerometers, and how we install them, what's the precautions, the journal bearing, the phase analysis, orbit plots and average shaft center line, the full spectrum transient state plots, rotor dynamics and turbomachinery malfunctions. We talk about the unbalance, pin shaft eccentricity, preload and misalignment, and this is the part we're going to talk about today. Excessive clearance, rubbing with partial annual rub, heavy, light, Newkirk and mortar effects, and also the fluid instability like whirl and whip, surgeon stall, electrostatic discharge, shaft crack, some instrumentation problems. So we cover lots of things in this course regarding turbomachinery, in addition to case studies. Thank you so much. I would like to thank Mobius so much for this chance and for this week of webinar, and to give us the chance to share the knowledge. So thank you so much, Mobius. So let's start. Because I have just one screen today, I might not be able to see the questions straight away, but like every couple of minutes, I will swap my screen to see if there is any questions. So the shaft preloads fault analysis. Like the preload is on directional steady state force acting on the rotor system. And we have preloads types. We have radial preload and we have the axial preload. The radial preload is a preload that acts in the direction perpendicular to the and through the center axis of the shaft. And the axial preload is the preload that acts in the direction that is parallel with the axis of rotation of the rotor. We have examples for the radial preload. The gravity, especially for horizontal machines, bearings preload, because the bearing design itself affecting the preload. And this was the main reason or the main cause of inventing or making different types of bearings to cause a certain amount of preloads to help the shaft stability. And we might have float preloads, internal misalignment, or external misalignment. This all types of radial preloads. And the axial preload, we can have a gravity, but for vertical machine, process thrust load, because of like the difference between the discharge and between the inlet of the flow, you might have some axial load, and also the differential expansion, which mostly happen on big machines like steam turbines. The effect of shaft preload can change in the shaft position inside the bearing, change in the machine vibration level and the frequency, change in bearing temperature because of the friction, could lead to secondary damage such as shaft crack or bearing and seal wear. Also, if you have high preload against the seals or the bearing exists for a long time, it will cause wear on the bearings. If the 2x components, which is a result of preload, exist for a long time, the shaft will be under high rate of stress reversal, which could lead to shaft crack. The misalignment will generally result in elevated vibration amplitude due to load transfer from one bearing to an adjacent one. The increase will show up as higher amplitude at 1x and 2x in the vibration spectrum, similar to any rotating equipment we analyze, like motors or pumps or gearbox, with 2x amplitude reaching or exceeding the 1x amplitude as the severity of the misalignment increases. The misalignment may be coupling or internal misalignment caused by improper bearing elevations. In turbomachinery analysis, we're not dealing just with a spectrum or waveform like we're dealing with motor or gearboxes or pumps. We have lots of other plots we need to consider and we need to have a look at before we do our analysis. Because when you do analysis for turbo machine, it's like a puzzle. You need to collect all the different clues and link them together so you will be able to know what's the problem. Elevated in 1x and 2x vibration amplitude, this is one of the indication of the misalignment. Oddly shaped direct orbit plot showing restriction in the motion, and we'll have a look on this and few examples. Shaft center line operating well away from the normal natural position with adjacent bearing showing opposite positioning. We have possible causes for this. Failure to probably align the coupling, incorrect accounting of a thermal growth. The different types of radial misalignment, like the interior misalignment and external, the internal misalignment can happen or caused by cooked bearings, cooked seals, bearing design, geometry, the curvature, flow instability within the impellers and diffusers. And the external misalignment can be caused by piping forces, pipe strain, foundation degradation, locked coupling, and misalignment. As you can see here, this is different orbit shapes. The one on the left side, this is orbit plot from lemon bearing. And guess what? This orbit plot is normal. When I say it's normal, I'm not mean it's completely normal to see it like this. But this orbit plot exists on this machine for more than 12 years with no problem at all. The thing is, this orbit plot is from double shaft motor. This motor is driving two gearboxes, and the gearbox is driving two compressors. It's an LNG plant. You have heavy shaft, you have lemon bearing. That's why you have more flexibility in the horizontal direction, less flexibility in the vertical direction, and you have less stiffness in the horizontal, you have higher stiffness on the vertical. And this is the main reason that the shaft is moving more in the horizontal direction than the vertical. And you see the orbit, as you can see. And if you look to the amplitude, is about 30 microns, peak to peak. It's not massively high. And the machine is running like this for many years with no issues at all. So very important when you do the shaft when you do analysis, you need to know the bearing type. And because the bearing type will definitely affect the orbit shape and will affect the shaft center line position of the shaft. So you need to consider the bearing type. If it's elliptical bearing, if you have tilt pad bearing, if you have just normal plane or cylindrical bearing, every bearing type has its own effect on the shaft position and the orbit shape and even the vibration level. The other orbit plot, which is that one, this is the heavy preload orbit, and this is because of the problem. You can see the movement restrictions and how the orbit is vertical, and even the levels here is, I believe, it's not very clear, around like 50 micron or something like that, peak to peak. But definitely this orbit shape, this is not the right one. Might have some motion restrictions causing the orbit shape to look this way. So when we start to do analysis, especially when you have a look on the many plots like vibration spectrum, shaft center line, orbit, the full spectrum, the cascade. So I prefer to put this as steps to diagnose the shaft preload. Number one, abnormal shaft orbit. One of the key elements of diagnosing the shaft preload is the shaft orbit. And the spectrum will show high 1x and 2x. Abnormal shaft center line position because of the effect of the misalignment. And also abnormal shaft versus casing motion. This need to be done by comparing the bearing cap vibration level to the proximity probe vibration levels. For normal shaft response, the casing vibration should be lower than the proximity probe. Also, the orbit shape should be very similar. In case of vice versa, if you have preloads, mostly you will have abnormal shaft to casing vibration as a result of heavy internal preload. And in this situation, you might see that the casing vibration level is higher than the proximity probe levels. And I will show you why, because we have a case study about this. Phase across the coupling would be out of phase, so you need to look for the phase across the coupling. We have different shapes for the orbit. The circular plot, not indication of good orbit. Normally, the normal orbit, you should have elliptical orbit because you have difference in the stiffness. And this is what caused the shaft, so the orbit plot to look as it is. So the elliptical shape, this is the normal. If it is heavily elliptical shape, this is not normal. If you have circular plot, that's not normal. If you have circular plot with high amplitude, this could be, for example, unbalance. With massively high amplitude with multiple dots, this could be oil web. You might have something called annual rub. It's not very common, very rare when you see something like that. But the normal shape, it should be elliptical orbit, which is the second one, that one. When you have higher preload, you will see the banana shape. More higher preload, you will see the H shape. And even you might see heart shape. There is many shapes for the orbit when it is heavily preloaded. As you can see, this is H shape of an orbit. You need to see the direct one, the 1x for the same orbit, you will not be able to figure out. If you look for the time waveform, you will see the time waveform from the Y probe is going up and down. And the distance around the center, you see the peak to peak is much higher. But with the X amplitude, you see how small it is because of the restriction of the motion. Same as here. And this is preloaded orbit as well. This example, it will explain many things about the shaft preload. This was from Olston gas turbine, 160 megawatt. And the bearing, you have journal bearing here. We used to, as MCS, used to do run up and cost down testing for this turbine every year as a part of the shutdown. And this Gas turbine is turbine driving a generator and the one shaft, no gearbox between them, and they're running at 3000 RPM. The vibration spectrum was showing elevated vibration at the running speed 1x and the second harmonic 2x. This is bearing 2. The bearing 2 is the drive end bearing of the turbine. And bearing 3 was the generator drive end. So we have bearing 1 is the turbine non-drive end. Bearing 2 is the turbine drive end. Bearing 3 is the generator drive end, and bearing 4 is the generator non-drive end. Both bearings spectrums, half spectrum is showing 1x and 2x. So this is the first clue. As you can see, high 1x and high 2x. Secondly, when we look for the shaft center line for bearing 2 and 3, you see massively, like bearing 2 especially, we have the shaft center line very near to the bearing clearance circle. And this means that the shaft is running very near to the bearing internal walls. And we must see high restriction of movement in this bearing especially. And when you look for bearing number 3, you can see the massive difference between the shaft center line position between bearing 2 and 3. And as you can see, the speed is changing on the shaft center line. And even this one, when it was starting, it was have some sort of preloaded on this bearing. It's not starting from the rest position. Okay, so this is a very good indication also that we have misalignment. So 1x and 2x and the shaft center line positions. Then one of the good things from the Emerson system, which is the MHM software, they have a good feature that you can make a 3D shaft animated. So from the time waveform, you can animate the shaft if you have the measurement at the 4 bearings. If you look, this is bearing 1, which is the non-drive end of the turbine, and this is the drive end of the generator and non-drive end. So we draw the shaft center line position, and you can see very clear or very obvious the difference on the shaft center line position between bearing 2 and 3, and this is a very good indication as well of misalignment. So we now have the spectrum, the shaft center line position, and the orbit. So this is the orbit of bearing number 2. We have from blank to bright, and this is the direction of rotation, so we have a forward precision orbit, but you can see how flattened is the orbit because of the motion restriction. And this you can consider it as some sort of D shape, so we might have some sort of rubbing as well. So we might have rubbing because of the high preload, and we have flattened orbit. And if you look for the time waveform, this is from 0 to the maximum positive peak and from 0 to the maximum negative peak. And very clear that we have huge amount of restriction of the movement. So this, the third evidence. So we look for the spectrum, shaft center line, and now the orbit. And this is also very tricky one. This is bearing number 2, the one which have very shifted abnormal shaft position and also flattened orbit, highly preloaded orbit, and this is the Boudet plot. So this is the Boudet plot for bearing number 3, the generator. This is the Boudet plot for bearing number 2. This is the first critical speed, second critical speed. If you look here for this Boudet plot, we cannot see the critical speeds. Is that turbine not running through any critical speed, like the speed is going up straight away? No, that's not true, because we can see the phase shifting here. So we definitely pass through a critical speed, So what happened here? What can drop the vibration at the critical speed? The factor is damping. And if you have very high damping, then the vibration, the machine, when you go through the critical speed, it will not vibrate or act as normal because the shaft is damped and have highly restriction in the motion. And when we say damping, we look for the eccentricity ratio. The eccentricity ratio, which is the difference between the shaft and the bearing diameters divided by the bearing radial clearance. This is divided by the radial bearing diameter, and this is what we call the eccentricity ratio. And the eccentricity ratio, when you have high eccentricity ratio, you will have high stiffness, you will have high damping, and you will have low fluid stability. So when you have low fluid instability, so when you have your shaft is running with high eccentricity ratio, the stiffness will increase, the damping will increase, and this is we need to focus on, and the fluid instability will decrease. When you have low eccentricity ratio, like if the shaft running near to the center, the fluid instability will increase, and the chances to have oil web will increase, but the stiffness will go down and the damping will go down. That's very clear. Like if we talk about the stiffness, when you have the shaft stiffness plus the bearing stiffness, both of them together will increase the total stiffness. And when the shaft is running very near to the bearing internal wall, it will drag some oil with it, and it will squeeze this oil on a certain position, creating the oil wedge, which will act something like a pillow carrying the shaft. And you have from one side the shaft weight and the gravity and the internal forces of the shaft, and you have the pressure of the oil wedge from the opposite side, plus some tangential force, and plus some other radial forces, and this will put the shaft in equilibrium position. This is more in the rotor dynamics. But come back to the shaft preloads. When the shaft is running very near to the bearing internal wall with high eccentricity ratio, you will have high stiffness, you will have high damping. And this is the case here. The shaft is almost at the bearing internal wall. That's why when you look to the Boudet plot, which is amplitude and RPM, phase and RPM, we cannot see the critical speeds because of the high damping. So this is a fourth thing. So we talked about and by the way, this is not the case every time. You might have shaft preload, but you still can see, but this is in the severe condition, this is what we see. So the spectrum 1x, 2x, the shaft center line, the orbit, and the Boudet plot. And if you look here for the shaft center line, bearing 1, bearing 2, bearing 3, and bearing 4. This is all of them. And you can see bearing 2 and 3, very obvious misalignment. This was the first case, and I like this case very much because it goes through all the points to explain what's the misalignment and preload and how we can diagnose them. This one is a bit special. This one was for a Siemens steam turbine. This is the HB, the LB, the gearbox, high-speed drive end, and generator. This is an old steam turbine. I've been called to do some data collection and analysis for this turbine. This turbine doesn't have proximity probes, and I used to take the readings from the bearing cap. The vibration from the bearing cap was about 8, 9, and sometimes up to 10 millimeter per second. And it was at 1x and a little bit smaller 2x. And I thought that we have some sort of imbalance. This is 11 megawatt Siemens steam turbine, 1986, a bit old. The customer has concerned about high vibration level at the LB turbine side, which was overhauled last time about 7 years ago. The rotor has been sent to South Africa for high-speed balancing. The turbine runs at 7,650 RPM at full speed, and the generator running at 1,500 RPM. The turbine is running above the second critical speed, while the full speed is very close to the second critical speed. This is Siemens 7,620, the shaft rotating counterclockwise. The critical speed is 3,560. generator speed 1500. This is the rotor weight, the rotor length, the drive end diameter, the journal bearing, the clearances, the bearing type, both are cylindrical bearing, and this is the rotor on the high-speed balancing machine. And this is the turbine casing. We have the HP, LB, bearing 1 and 2. This is the steam turbine, and this is your gearbox and the generator. At this survey, vibration proximity probe have been installed for more accurate vibration assessment and diagnostics. We installed 4 radial proximity probe, the 3300 XL 8 mm with 9 meter proximity driver, in addition to 1 key phaser as the reference for the phase. Measurement and speed detection. A notch has been made on the gearbox high-speed output shaft. This turbine doesn't have anything. It's very old, but we was lucky that there was a spot on the. We are getting a little feedback from the mic. Sorry, I can't. Okay, from the mic. Sorry. Okay, so from your mic. Okay. Okay. Sorry. Is it better now? Can you hear me better now? A bit better. It's like a vibration when you speak. Okay, I will try to. Sorry, because when I'm talking, I'm a bit moving my body too much. Okay, I will try to not to. Okay, thanks, Kim. So, vibration has been collected from proximity probes, because this is an old turbine and doesn't have any proximity probes. So vibration has been collected from proximity probes installed on the turbine bearing, drive, and non-drive ends for detection and evaluation of the relative displacement. We was lucky that there was already some holes on the bearing caps, which enable us to install these proximity probes. X and Y are installed, those probes, while probe X is the first probe and Y was the second probe after 90-degree counterclockwise from the driver, which is the turbine, to the driven side, which is the gearbox. Vibration has been collected from the turbine bearing caps using velometers as well. The velometer channel are designated as channel H and V, which is the horizontal and the vertical. We use the ADRI, the 208 channel analyzer has been used to collect this data, and also use the Contest VB7 to collect the data from the bearing cap. As you can see, we was lucky to install the proximity probe because there was a hole already on the bearing cap. So we have 2x and 2y and 1x and 1y from the two sides. So we install the proximity probes. And for the key phaser, we make a hole from this part coming from the gearbox, part of the shaft, and we install the key phaser this way. So we'll be able to collect proper data from the machine, because taking the data only from the bearing cap wasn't the solution. And then we have this junction box installed outside with buffering output BNC connection, 4 outputs for the 4 radial probes, and 1 for the key phaser. And everything is connected with the ADRI. So we have 4 probes as proximity probes, and we install, as you can see, the velometers on the bearing cap at the same time. So we collect casing data and we collect the journal bearing data. We was expecting to see high radial vibration from the relative displacement vibration from the probes, because the thing is, the casing vibration was really high, and we thought that also the proximity probe vibration or the relative displacement will be high as well. And even all my thoughts was going to the unbalance. Sorry guys, just 1 second.
Thank you all so much. If we could just give Salah one moment, he's got to attend to something real fast, but he will be right back.
Hello, can you hear me now?
Yes, we sure
Yes.
can.
Yeah, sorry, my Bluetooth headsets is run out of battery, so I came back. That's good.
Thank
Okay.
you.
So as you can see here, this is the 1x and 1y probes for the turbine non-drive end, and the orientation was 45 right, 45 left, relative displacement, and we have 2x and 2y. We have the tachometer, and then we have the 4 velometers on the bearing cap. And as I just mentioned, I thought that the vibration levels will be way higher from the relative displacement probe, because we were talking about like 9 millimeter per second or something. However, this was the readings from the proximity probes: 17.5 microns peak to peak, 19, 25, 28.1. This was the highest level, which was really low. And even the vibration at 1x was 11, 13, 20, 22 microns peak to peak. But when you look to the bearing cap vibration for the turbine, was 3.9, 1.8, 1.4, 5.2, 3.8. So it was really high. And some occasions when this was at 7.5 megawatt. And as I mentioned, the 11 megawatt was the maximum load. And we cannot run the turbine to 11 megawatt, because when we do this, the vibration levels increase. And when we saw this high bearing cap vibration and the low relative displacement, I start to think about misalignment or preload. The bearing cap absolute casing vibration measurement indicated that the package is classified as Zone B and considered unrestricted for long-term operation. But this was at 7.5 megawatts. But when we increase the load, the levels go higher. So when we look at the vibration spectrum, it was showing 1x and lower 2x. This is the bearing cap. And the bearing cap 1 and 2 showing elevated vibration at the running speed 1x. This is the running speed. And this was the 2h, 1h. And this was the 1v and 2v. So this is all the bearing cap vibration, as you can see here, 1x and the smaller 2x. And this one here was the proximity probe readings. As you can see, 1x, 2x, 1x, and 2x in the forward precision was higher amplitude, but 2 was smaller, and the dominant vibration was at 1x, but as microns was very low. But this was a cylindrical bearing, and cylindrical bearing, as you can see, the shaft is rotating counterclockwise. Here, the shaft is rotating counterclockwise. While the shaft is rotating counterclockwise, normally we expect to see the shaft center line go to the right and be in this position, not going straight up vertical as it's doing. So this is the first thing which came into my mind. Like, we have abnormal shaft center line, we have high bearing cap vibration comparing to the relative displacement. When you look to the orbit, it was preloaded orbit. Yes, the amplitude wasn't high, but you can see a preloaded orbit. And this is what we call a bit similar to kidney shape or banana shape. So we have high preloaded orbit or preloaded orbit shape, not normal orbit shape. We have abnormal shaft center line. We have high bearing cap vibration comparing to the relative displacement. And then we decide, okay, we will check the alignment. And yes, this was the case. The machine was out of alignment, and Siemens guys, they came to check the alignment, and vertical, the turbine low as per specification, and this should be the levels which should be checked. And this was the findings for this one was there was like many recommendations to check the internal clearance, the radial clearance of the bearing, and to check the hold down bolts. And this was here like the turbine hold down bolt. The front turbine bolt was adjusted with the clearance. Second one was the clearance. As per specification, type 1 hold down bolts can restrict the turbine from moving the conjunction with the thermal growth. So the thermal growth has also some effect on this while the machine is getting more hot and on higher load. Also the misalignment increasing. And the machine was above the maximum design was about 0.02 millimeter. Front radial bearing clearance was 0.17 within design specification. And when the Siemens guy, they came, they check all the measurements, and the level was 0.42, while it should be 0.2. So we have about 0.2 millimeter outside the tolerance. Once this all has been adjusted, the vibration levels dropped, and they managed to run the machine to the full load with no alert or no trip. And this was the second one. So the thing is, we need to learn from this second case, which is you need to be careful about the difference on the vibration reading from the bearing cap and the relative displacement. Now the thing is which we need to talk about why the bearing cap vibration is high with low vibration and relative displacement probe. Like the thing is, if you have, for example, this is your journal bearing and your shaft is here, for example, and you have two probes. Okay, so the shaft is rotating here. How the proximity probes work? It works with the voltage gap, and the change in the voltage gap will be translated to vibration. But if the shaft is squeezed here, it cannot move, and it is preloaded to stop at this direction because of high preload, because of misalignment, because something restricts its motion. So the shaft have lots of energy inside it, and because it's near to the bearing cap, this energy transfer to the bearing cap, causing high vibration. You can feel it on the bearing cap. While the restriction of movement, because this shaft is by decoupling somehow and was installed in this position, and it's misaligned, so the shaft will not be able to move freely inside the bearing. If you're trying, the shaft's like trying to move at this direction or this direction, it can't because of the restriction of the motion. But on the other side, it's very near to the bearing cap, and they can transfer lots of vibration energy to the bearing cap, and then you can feel higher vibration in the bearing cap. So that's why you need to be careful when you collect vibration data for turbo machines. You need to collect the bearing cap vibration as well. Not enough to say, okay, the proximity probes are good, it's journal bearing, I don't need to collect bearing cap vibration. But no, you did, because simply, if you only depend on the proximity probe, this machine is perfect, good, within the limits. But when you look for the bearing cap vibration, it's higher. There is many factors. If you look for the turbine design itself, there is here this bolts here, and there's this bit old photo. There was like jack bolts on the sides, and this jack bolts was very tightened, and when the turbine getting hot, it need to move a little bit. This jack bolts wasn't enabled. They added this photos is been taken before they add the jack bolts here, which been used to do the alignment, and this was also another problem, that this jack bolts affecting the thermal expansion of the turbine, which is increasing the misalignment problem. I believe that's all from my side for today, and I hope it was a light session and not heavy. And yeah, if anyone have any questions or anything from my side, I'm happy to do.
Oh, thank you so much, Saul, for your great presentation. And like you did say, now is time for the question and answer session. So if you do have any questions, please go ahead and enter them now and submit them for Salah to answer. We will try to get to all of your questions live here today. Again, you will be anonymous when we call out your questions. And then if we don't happen to get to all of them, we will make sure Salah reaches out to you after the webinar today. So, when you were early on in your presentation, you were on the shaft protocols misalignment. And this first question is asking which software is used to draw the center line position in 3D like you did in this example?
This was the Emerson MHM software. The device was 2600, the multi-channel analyzer, and this is the only one I found can do this.
Oh, thank you so much for that. And
Thank you.
same case study here. Why the probes are attached at a difference of 90 degrees. And they're asking, why not 180 degrees?
Because the thing is, this, as I mentioned, was an older machine, and this was the only holes was available for this bearing design. And the most important thing was the two proximity probe to be 90-degree apart. In some, yes, in some situation they can be more, depend on the bearing design. But at this situation, we only had this a chance because we already have a holes was drilled on the bearing caps, and this is the one we used to install the proximity probe.
Great. Thank you. All right. Well, one person is again thanking you so much for your presentation. And about the case, I'm going to do my best here, but I also might chat this to you because you might know the numbers a little better. Um, they say N01. It seems that the BRG2 is more impacted than the BRG3 by misalignment. This may influence the analyst. Any explanation about this?
Yes, I believe you're talking about the first case study. I believe you're talking about this one, that the bearing number two was influenced more on the gas turbine more than bearing three. Is that correct?
Give me one moment here. I'm going to pull back up your screen. And if we do hear from this person again, we will happily let you know if it's the correct one. But based on what they are saying, I do believe this is the correct string with the two different bearings on it.
Yeah, because this was the only one. Yes, the bearing number two, it looks like it's affected by misalignment more than bearing number three. And this is what is the misalignment is. You might have one bearing is affected more than the other one. All depend about the installation. All the bearing types are the same. In this case, all the bearing types was the same. Like bearing 1, 2, 3, and 4, all of them was the same. It just it's happened like many things can affect this, like the speed of the shaft, the weight of the shaft, the amount of the misalignment, the temperature on the turbine different from the temperature on the generator. So all the things can affect the shaft center line position.
All right, sticking on this screen, the same person was saying, um, can you have a preload in case of unbalance? They are seeing the preload on the 1x filtered vibration.
Can you have preload in case of unbalance? Like if you have unbalance, well, I didn't get the question that much. Like
Yep,
you mean,
you're good. So I'll back up to their original one here. Is the uncentered time wave a form of preload?
yes, uncentered time waveform like this one. This what you mean? Like the time waveform is not symmetrical? Yes, this is
Yes.
indication of preload because you have from zero to the maximum amplitude different from zero to the maximum negative amplitude because of the movement restriction. Unbalance itself, the unbalance itself, it can be considered as some sort of preload. And a quick example for this, I did balancing for a steam turbine before, and vibration levels dropped massively. And then when we run the turbine again, we got oil whirl. Because when I did very good balancing, vibration was about 4 micron and 3 microns peak to peak. There was no vibration at all. And because of this, all the load or the preload on the shaft is gone. And because of that, the shaft has oil whirl and vibration became very high. When we run the machine again, I thought the unbalance, I did a mistake. Then when we run the machine again, I looked for the spectrum and it was subsynchronous peak and it was the whirling frequency and even transferred to become oil whip. The shaft start the movement and then go to the right and then it go to the center of the bearing. And we know that because we did a very good balancing job. And to get rid of this, we added 10 grams of weight to create unbalance on the shaft. And when we created unbalance, it gives some preload, so the shaft pushed away from the center, and then we get rid of the oil whirl and oil whip problem. So the unbalance itself, if this is your question, the unbalance itself is some sorts of preload. It can be considered some sort of preload. But I don't say it's a good preload, but it's within limitation. If you have too much unbalance, you have very high vibration. But the unbalance is some energy or some sort of preload on the shaft to avoid the shaft running in the middle. There was very famous case study from Mobius in category 3 for condensate extraction valve when they did balancing for it, and then it was very good balancing as well, and the shaft and all the load on the bearing is gone, and because of this, the bearing start to skid. And when the bearing was skidding because of the friction, the grease evaporated, go inside the vertical motor, and then it's exploded. It was in one of the power stations here in Australia. And this is the similar thing.
Well, thank you so much to diving into that question. All right, guys, these are great questions coming on. If you do have any more, Salah does have a few more moments here to answer them. So, moving on to this next question. Can the cap vibrations be simply measured using a vibrometer using an accelerator probe?
Yes, it can be measured definitely by accelerometer. In the case I showed you, the second one, I used the verometer, but definitely can use the accelerometer to measure the bearing cap vibration. But for journal bearing, definitely you need proximity probe. This is 100%. Journal bearing, you need proximity probe so you can understand the movement of the shaft. And it's very also like people say, journal bearing will do only proximity probe. No, with journal bearing, you need to collect relative displacement data, not displacement, relative displacement data, and the absolute casing vibration data. You need to collect both of them.
Perfect. Thank you. Can you explain about acceptable region that you were showing, I believe, in the last case study? What is the acceptable region?
Okay, for any machine, especially turbo machines, we normally I'm using two standards: the 816. This is for absolute casing vibration level, and 7919. If I have a good memory, 7919 for the relative displacement. We have four zones: zone A, B, C, and D. For zone A, the vibration level we say from, for example, from 0 to 90 microns peak to peak. Vibration is in zone A, which is good, no problem. From zone B, from what I remember, from 90 to 165 microns peak to peak. And from B to C, it's from 165 to 245. This is zone C. And above 245 microns peak to peak, this is zone D. This is the four zones for relative displacement vibration, but be careful. If the vibration level, for example, you have a steam turbine, and this steam turbine was running with about 25 micron or 35 micron peak to peak, then you had overhauled this turbine, and it came back with vibration about 85 microns peak to peak. So it was 20 and became 85. 85 microns peak to peak, you're still below the 90 microns peak to peak. So you're still in zone A. So would you accept this machine? And the answer is no. Because if the vibration levels increased with about more than 25% of the original vibration, even if it's still in the acceptable level, you should not accept that one. So this is for the relative displacement. For the casing, we say that 2816 from 0 to 4 point, so 0 to 3.2, what I believe is okay or acceptable. From 3 up to 7, this is acceptable, but high over than 7, this is unacceptable.
Perfect. Thank you. All right. We're going to probably finish things up with two different questions here for you,
Take your
last.
time. I'm free for any questions.
Okay. Thank you. So this person is specifically relating to example 21. They are saying it seems that vibrations were increasing with the power. Usually, this is not linked to an unbalance or a misalignment. What could be the reason?
You mean vibration increasing to the power and not
Not linked to unbalance or misalignment.
normally it's not the right term. It should be load, increased related to load, not power. It should be like with load. Normally the load affects, if you have very common thing in generator which called thermal imbalance. So this definitely increase because of this. You might have the preload, which is the misalignment, or you have the secondary damage or secondary problem, which is the rubbing. So if you have the rubbing, this increase the vibration, but the rubbing is all the time, or the rubbing is considered as a secondary damage, happened because of unbalance, happened because of runout, happened because of eccentricity or shafted preload. All this can cause rubbing, and the rubbing will increase the vibration and increase the temperature. So the most common things is the misalignment or the preload and the unbalance. This is very related to the load or the power, and the secondary damage related to them, which is like the rubbing, can happen as a result of unbalance or misalignment, and also this will increase the vibration.
Thank you. Okay, going to another slide that you have on slide 19 of the orbit figure. Apart from the misalignment, was there any wear problems?
Yes, the bearing number 2 have some sort of light rub has been found on the bearing. I don't have the photo for it now, but I'm very happy to share it with anyone. Can reach me on LinkedIn or something. I'm very happy to share that one.
Thank you. All right, this one might be a little number teaser for you, but
Okay.
do you know the ISO for the displacement readings?
The ISO standard for the relative displacement is 7919, and you have 4 zones A, B, C, and D. 0 to 90, 90 to 165, 165 to 245, and over than 245.
Okay, well, that was not a number problem at all for you. You had that memorized. All
Yes.
right. How do we qualify the difference between two shaft positions on the center line plots? And how can we tell that that difference is okay? And they're talking about across the couplings.
Okay, this is a bit tricky. There is no an exact standard for this. So you need to use your engineering sense as an analyst to see the difference in the shaft center line positions. Like if, for example, they have 10 microns difference or like 15 microns difference, that's not a big deal. But when you look between them and you have more than 100 microns difference, you see one of them in the fourth quadrant and the other one on the first quadrant, one them at the bottom of the bearing to the left, one at the top to the right. So definitely they away from each other. So this is the way you consider this. Like, for example, the same like you can see here in this shaft center line plots, you can see this one So definitely, like if you divide this to 4 and this is to 4 like this, so definitely both of them are in two different quadrants. So this way we'll say, okay, definitely these two are away from each other, and we definitely have some sort of misalignment here. Or similar like to this one as well. You can see here, like if you make this as 4 here, and this is your shaft center line position, and this one, so it's totally away from each other.
Thank you. All right, so we are going to wrap things up with one last question here.
No worries.
This person is asking, when they find unbalance or misalignment, is it mandatory to change or inspect the lubrication?
Mm, I don't think so. I don't think so. This is something you need, like the lubrication, for example, it need to be checked anyway. Like I have one of the power stations. It's one of my customers' power station, and we do every 3 months check for the oil for 4 big turbines, 375 megawatt, and we do all the required tests like the RBVOT, the roller test, the color test, the foaming test, the TAN, the particle counts, the BQ index, the contaminants, the FTIR, all the package. We do it every 3 months, and this is quite enough to check the oil condition at all over the whole year. Any more questions, Gab?
No more questions that have come in currently. We are a bit caught up, but I will go back through the list. Anyone, again, if you submitted a question we didn't get to, we will forward this on to Salah so he could answer that for you. Again,
Sure.
I want to thank you so much for a great presentation. And you did mention this a bit earlier, but if somebody would like to reach out to you or find more about you, where could they do that?
LinkedIn, I have now 22,300 followers on LinkedIn at the moment. So any, anyone would like to reach me, I'm very responsive on LinkedIn and even my phone on LinkedIn. So if someone wants to reach me through WhatsApp, emails, so I'm pretty easy person to reach. I might have some delay with the reply because I'm very busy, but I will reply. Like I never ignore anyone. So if you have your question, if I didn't reply to it straight away, just give me some time and I will do.
I do agree. You've answered everybody's questions from past webinars, so I do know you get back to everybody. And thank you so much
Thank you.
again for today. Well, just a few more helpful hints for all of you guys before we do head out today. As a thank you for attending WOW, we are pleased to provide you with 50% off your conference pass to the CBM and Reliability Live training conferences happening Mexico in August, and Australia in November. You can use code WOW50 to reserve your seat and take advantage of this discount. These events include certification training opportunities, hands on workshops, case study sessions. You can visit MobiusConnectConference.com to learn more about these live and in person events. And you'll find a link to register in a follow up email after today's webinar. All right, before closing out, do you have anything else that you'd like to add today, Salah?
No, all good. Just for the Perth conference, which is in the coming November, I will be a speaker on the conference. I will talk about very nice case studies for remote balancing. I did balancing for a turbine in Turkey while I'm in Australia. It was 155 megawatt steam turbine. I did this the balancing for it remotely over this very long distance, and it was really very challenging, very exciting case. So I would be very happy if anyone would like to attend to the Perth conference with Mobius, and he can not only be, he can watch many presentations from many talented and skilled condition monitoring guys from everywhere around the world, and I will be one of them. Thank you so much. Thanks everyone. Thanks for whoever attended.
Oh, thank you so much. And we are so pleased that you were a speaker. Again, anybody who wants to go meet Salah, see him in person, head to the Australia conference. Use your code WOW50 to save 50% on that ticket. All right. Well, WOW is not over yet. We still have 2 full days of WOW. Our next one coming up in just about an hour, reliability and maintenance optimization issues for industrial processes. If you guys didn't register and you'd like to attend, just go back to your attendee hub. You're welcome to click on the webinar. Should be up in just about an hour or so. Again, you can also visit Mobius Connect on LinkedIn to find the link as well. And just a quick reminder, look out for an email from us with the on-demand version of this session and your certificate of attendance. If you are interested in engaging with other industry professionals or you would like to participate in the industry's live feed and forums on Mobius Connect, visit mobiusconnect.com to create your free profile. Make sure, again, you follow us on social media at Mobius Connect to stay up to date with the latest community happenings. And if you do have any questions at all, you can email the Mobius Connect team at info@mobiusconnect.com. Thanks again for joining us. Have a great day. Stay safe, and we will see you all next time.
Thank you.
Thank you.